So please take your seat. Please, put yourself in the comfortable position. So we'll be walking a little bit through the topic of ML and using TinyML for embedded products. And tonight it's me, Alexander Lubimov, Business Director of EKTOS Development, and Darina Nedilko, who is our data analyst, and she will be helping us to dive into the real mechanics, which is under the hood of the ML tonight. So that's the plan for now. So let's get moving. First of all, I would like to briefly introduce who we are. EKTOS is a Danish-born consultancy. Basically, it has been started back into 2007 by two engineers in a city called Viborg in Denmark. And since that time, we became like 120 people roughly, doing different kind of electronics development, manufacturing, the contract manufacturing of electronics, as well as type testing and approval services worldwide. So that's what we do. We have overall 6 offices around Europe, where we have 3 offices in Denmark, and then we have 2 offices in Ukraine, where we recently resumed our office in the city of Kharkiv, because it became more safe now, and we have few development people who are not leaving their native city. And then we started new development office in the city of Maribor in Slovenia, where we will be looking into our further expansion of the development team with particular skill sets related to power electronics and IoT business. So far, I'm representing the biggest business area, which is electronics development, 53 engineers. And overall, we have been doing a lot of different projects, but if you take the Internet of Things projects recently, we have been doing like 50 projects with different technology sets and stuff like that, reaching to the budget of roughly 40 million Danish crowns. So that's a little bit about us. Okay, let us look what we'll be talking about today. First of all, we will be talking about machine learning and understanding what machine learning is about, a little bit diving deeper into what is behind the term machine learning, and also moving slightly to the way machine learning is used in embedded. So what are the peculiarities, why the TinyML is different from ML and stuff like that. Then we will be concentrating a little bit on the real case study, so discussing one of the most recent projects we had with my team. Then we'll talk about process, and a little bit touching the problem of how actually manage embedded machine learning projects. What are the differences? What are the peculiarities of those projects? Then we'll look into kind of understanding if you can use TinyML for your products and projects. And then we'll wrap this up with a wrap-up slide, and just also highlight what's going to be next activity we're going to present. Actually, it will be also in the machine learning topic. So let's talk about machine learning as a design paradigm. And before we go into that, I would kindly ask you to put a plus sign into the chat box if you have already been doing some ML projects, and specifically TinyML. That would be interesting to see if you guys have already been developing this kind of technology. And I will be continuing talking about what do we call ML a design paradigm. So first of all, let's let's go back to the problem solving complexity. You can see here on the right side of the screen, we have different complexity of computation or algorithmical tasks, starting with classical polynomial complexity. That is also known as O notion of the algorithmic complexity. And then we go to the non-polynomial complexity, and then we kind of climb up to non-polynomial complete and non-polynomial hard complexity. So if you look into typical way we design control algorithms or data processing algorithms, how does it work? It works very simple. You sit down, you take your pen, you take a piece of paper, you write down your imagination about how you want to process the data, how you want to kind of do data fusion. Then you make a flow chart, and then you program it, and then you're good to go. You alternate here and there, you check it, you debug it, and then it seems to be okay. Well, that's true. Unfortunately, it works only for P complexity tasks. And when I say P complexity tasks, it could be something like, let me put it this way, finding a common divisor for the set of different numbers. So you have a subset of numbers and you want to find a common divisor. So that's a typical polynomial complexity. When you move up with the complexity, non-polynomial. And one of the classical examples of that task would be, the traveling salesman problem, where you have a map of different cities, and you want your salesman to visit every city, and then visit each city only once, and then do it in the most optimal way of spending his time and mileage. And when you move to non-polynomial tasks, then actually foreseeing the complete algorithm just with a pen and piece of paper is getting a little bit more complex, because you can apparently come up with some sort of top level ideas how you want to solve the task, but in reality it takes a lot of time to kind of calculate also different complex exclusive branches of the algorithms, and then you want to also solve some exceptional branches of the algorithms and stuff like that. And that's going to be pretty complex. Actually, you cannot just put down the whole algorithm from the one try, unless you have a whole department of algorithm people who are working full-time on algorithms. And then when we move with the complexity to NP complete and NP hard, basically it could be described very simple. It's just NP complete is the most hardest task among the NP complexity, and NP hard is the most complex task or subclass of tasks from NP complete subset. So it's actually pretty hard task. And one of the examples of NP complete task could be like if you have a subset of different goods in your grocery shop, and then you want to sort those goods according to their weight and value. And then you have a trolley where you want to put a lot of different items, not to exceed a particular weight, but then for the specific value. So it's kind of, now we are talking combinations, and combinations are normally also, or the combination-based math is normally pretty complex as well. So that's the good intro to start understanding that not all tasks can be solved in a classical, I would say, perspective, deterministic, and sequenced algorithm, as we discussed, P can be solved with. Instead, what you can do, you can examine your data. You can try to simulate with different sensors, with different use cases, what kind of data input you are getting from the amount of sensors, from the real case scenarios. And then instead of trying to solve this problem from the beginning, you just let situation run. You let to actually collect the data and write down what happens with your control system, or with your network system, or with your data handling system. What happens? What kind of outputs you are getting when you are making the data fusion? What do you expect? And then when you actually put into this kind of paradigm when you put an observer, so to say, and that's normally data analyst who is represented today by Darina, and then you put their know-how person, and that's normally in our case custom, because we are not solving the algorithmic tasks for our clients, but we are solving more engineering tasks, development tasks, where customers are representing the know-how. So that's the paradigm. That's kind of moving from the hardly sequenced algorithms to data flows, to understanding the input data, what happens with the data when it goes through the control system, or through the, I would say, data management system, and then trying to see, okay, what actually happens with the data. Good. So we have this concept described, and then what happens next is that it's really important for you to basically collect your data and understand what happens, how you can see, just by simple plot like the one I'm pointing on right at the moment, how you can use this plot of the data, meaning that this could be a result of your algorithm, pretty simple algorithm, or just data popping up from a sensor. How you can see the connection between these different, I would say, islands of the data. And that's the whole thing about machine learning, that you get your data plotted, and then you start looking into what kind of data patterns you can see. And basically, in machine learning, the first part of the process that is quite often called labeling as the most complex task is that you identify these islands of data. You look into what is happening with the data plots, and then you kind of group the data into clusters. Let's put it this way right at the moment. So that's what happens. That's really important to understand your data. And then let's for the moment look into typical tasks where you can say, okay, this is definitely for the machine learning. I would say we can break down to three major tasks. Well, the first major task would be regressions and forecasting. You can see if you have some kind of plot of the data. We have some historical data, and then we want to guess. In the sequenced algorithms, it will be like a polynomial prediction, or the continuous approximation between different dots you already have in the history of the data set, and then just trying to understand what happens next. The second big task for machine learning is actually classification, where you ask your algorithm or the data model to do classification and splitting of different objects to several categories. If it's just a binary yes or no, so to say, classification, then it's binary classification task. If you have more instances of data you want to classify to, then you have in class classification model. And the third big task, which is normally well, that's probably the big one you have heard about before. That's called anomaly detection. And this anomaly detection is quite often used in predictive maintenance and looking into kind of wear and tear of different systems like motors or vibrating machines, whatnot. So these are the three main tasks you can address with the machine learning. But sometimes it's not really obvious to understand to which one of the pillars your task belongs to, and then let's talk about it a bit more so you can better understand how to actually put into which bucket you can put your task on. Okay, well, what is TinyML? So far we have been just talking about machine learning as a general thinking paradigm. What is TinyML? Well, TinyML is a very simple fusion of actually using the classical machine learning algorithms, connecting them with small or relatively small computation footprint embedded devices. And then it can be something like, Raspberry Pi. It can be even smaller, like ESP32, and it can be also 8-bit STM8 by ST microelectronics processor. So that's actually how you mention the embedded device and the small footprint. And then basically what happens next is that you connecting these two things, you get to the classical TinyML or embedded ML, as it's called. And that's what we'll be talking about during the next part of our webinar today. Well, if you look into decisions and if you look into the data, what do you get from the TinyML? What is the reason behind actually doing all those edge computing tasks, as they call them? And by edge computing, we mean that we actually push as much as possible calculations and decision making to the edge node, to the small embedded product, rather than collecting all the data, pushing them to the cloud server, and then making a decision at the cloud server side. So what are the challenges and benefits implementing tiny machine learning in embedded? Well, the benefits are obviously you can just get to the low power consumption, because you can use tiny products, battery powered, to collect the data whenever data is available, and then your the global energy footprint will be relatively small. Then you have real-time processing, meaning that you don't need to kind of upload all your data to the cloud, and then the cloud is busy with servicing something else, and then you have to wait for the decision to happen. So it's actually pretty fast with TinyML models, where your edge node or just small embedded product can make a decision that the task is properly classified and can be solved. You have privacy and data security, obviously, because you're not pushing data back and forth between cloud and the embedded product. Well, environmental impact is something what actually resonates pretty nicely with low power consumption. So you're not using excessive resources, and it's pretty cost effective, because you're deploying those embedded products anyway as massive deployment. Let's say in IoT world, you have so many sensors around. So and you don't need to scale up and do crazy scaling up of cloud computing power and stuff like that. But what are the challenges? Well, the challenges are here as well. First of all, we have data quality and need of data redundancy. What does it mean? Basically, if you need to have great working machine learning model, you need redundant data. So you can actually make sure that your data is good enough to be able to make a decision on. So instead of let's imagine the temperature sensor that is sitting on the wall somewhere, then the decision about enabling the heating, the floor heating, can be just one set point, basically comparison. If temperature is above 18 degrees or below 18 degrees, then you turn off the heating. In machine learning, because you need to train your model first of all, and secondly, you want to predict when actually, for instance, you have to turn on the heating, you need much more data. And that's one of the challenges, because you want to collect more data, obviously. Then you have resource constraints. Well, that's clear, because normally TinyML models, they're based on neural networks, and apparently you have to use a particular amount of RAM and flash for the footprint of your application. And in case of very small embedded targets, you obviously have to plan for that. The lifecycle management, basically meaning that if model evolves, if you want to change the model, you obviously have to push a new firmware. So you cannot just kind of adjust something in a setting, saying, okay, now the set point is when floor have to be heated up is this, that, but you have to kind of retrain the model and push the model metadata. And normally it's in the data footprint, it's pretty comparable with the firmware pushing over the air. And then we have interoperability thing. Let's say you have a set of products where you want to implement the same ML model, then obviously you have to port the model into each different target and make sure that it actually works properly. So these are the benefits and challenges of using TinyML in embedded. Okay, so let us look into the use case. Well, it's a lot of text, but let me just very briefly move you into the idea here. Well, we have the classical for today. It's very typical product to assess the indoor climate. It could be just your bedroom, or it can be a hotel room, where you have a smart sensor with measurements of the parameters like humidity and temperature, different parameters like VOC sensing or CO2 measurements. And then in our particular case, we also have digital microphone available for actually listening for different and looking for different sound patterns, what's going on. And a small thing we had also was light sensor, so we can obviously detect if light is on or not. The task we wanted to solve basically was related to the classical data fusion model, where you using a fixed amount of sensors, where you want to assess what is actually going on with the climate. And one of the tasks we were kind of tasked with was to assess if the cleaning of this particular premise was done in a good way, or it was actually not done properly. And that's what we wanted to look into. That's what we wanted to try to investigate, looking into the data we have available. So basically, the questions we had addressed were like, if humidity was changed properly, if the cleaning step was using any specific detergents to clean, the table surfaces and rooms and stuff. And the last but not least question was like, if we actually had HVAC system, the ventilation system for the premise stopped during the cleaning, so we are not pushing the pollution into different rooms. And what customer wanted at the back end is not all this data about how the humidity was changing over time, how many volatile particles were detected and stuff like that. Basically, what the customer wanted is just to have a kind of pass score, good or bad cleaning was happening, and also based on that, the cleaning schedule was updated for the room. It's specifically working fine for the big for the big premises like hotels or some big, for instance, hospitals, where you have to clean every room. So you have to actually put some kind of pass mark for each room, and then generate the schedule of cleaning. And the last important thing, what I want to stress your attention on, is that as the product we have been developing was based on BOT technology, we were actually pretty stressed with the data traffic footprint. So we were not just pushing tons of data. We cannot just push in real time the data set that we get every 10 seconds or 1 second. So that's why we wanted to go into the TinyML mode. And basically, what you can see on the screen here is more or less like a problem statement put into the few sentences, and you can see here on the left side also kind of the top level picture. How do you get to the data? You can see that we had some plots of different parameters, and you can see that we were looking into actual cleaning happening, just initially by eyes, later on by tools, and this is where the Rena will kick in now. But that's how it works with the data labeling. Basically, you can obviously understand where the cleaning was happening, because you know what kind of parameters changing and stuff, and that's the way you normally start working with your data. So moving on to the next slide, I want to pass the microphone to you, Darina. So please go ahead.
Hi everyone. So let's talk more about tools and how to do this, how to implement it using deep learning techniques. Okay, so development of TinyML solution includes three main phases or stages. First stage is the most important. You should take care of your data. You should really investigate it. It includes data processing stages, feature selection stages, data labeling stage. There are actually plenty of annotating tools online. You can see them. STM even has one, but to know more during our next webinar. But we used our self-made scripts, Python scripts, to annotate the data. Phase number 2 is model development and experiment tracking. It also includes fine-tuning our model and evaluating the results. You can see here that we used Google Colab as our main environment, and we used Python as primary language, employing TensorFlow and Keras APIs to build and train models. You can also find your own tool. You can use any other notebooks. For example, you can do it on your local computer, or you can use AWS tools as you wish. And the last phase, phase number 3, is porting. Since we used ESP board, we employed a ESP IDF platform and C language to make model quantization and porting to the device, and of course testing the results. Can you please click to the next slide? Yeah, okay. As you already know, as you already heard, there are 3 main tasks we can solve. But let's fit it into our case. So if we are talking anomaly detection, what we want to see here, we want to see if data is behaving regularly. So when we're talking about anomaly detection, we're detecting anomalies and trying to find some irregular patterns occurring. It's not our case. Let's go to the regression. When we're talking about regression, we're doing some forecasting. As you could understand, it's not our case at all. So we are moving to classification. Could you please do the next slide? Click. Yes, great. So classification. What we need to do is distinguish whether cleaning is happening or not, whether it's good or not. So here we can clearly see 2 classes we need to find. And it is a binary classification because we answered the question, is cleaning happening or not? Yes or no. Can you please click next slide? There are many architectures to use to employ for this task, but regardless this variety, please click next slide. We will mainly focus on 2 architectures like FNN, perceptron model, feed-forward, trained using backpropagation technique, and convolutional neural network. Why did we use it? Because of course, of memory shortage problem. So you can see here that FNN is the most simple model in deep learning. It's faster to train, and all the operations are supported by TF-Lite framework. When we are talking about convolutional neural network, we can also notice that it employs a convolutional operation. Can you please click the next slide? So what is perceptron? Perceptron is a artificial neuron. It's like in our brains, but happening in our computer, programmed by people. A single neuron is a set of weights and biases, and of course an activation function, which makes relations nonlinear and enable them to mimic complex relations in data. You can see here on the top right corner a graphic. It's the results of our model. Here we can see that balanced accuracy is 96% and F1 score is 87%. Why did we use these metrics? Because in real world, of course, data isn't balanced. And these metrics help us to understand clearly how good our algorithm perform. Could you please go to the next slide? So what is CNN? CNN, as I said, it's a convolutional neural network, and the key part of it is a convolutional operation. Of course, it also incorporates some feed-forward layers, but as a first steps of working with data there is making a convolution. This architecture enables us to see our data as a picture. So this, to be precise, this model often used as a tool to tackle image or video problems. Here you can also see the performance. Yes, and that's all. Thank you.
Thank you, Darina. So basically, to wrap up this short presentation, we had used two models. We tried both EKTOS feed-forward neural network and convolutional neural network to experiment which model will give us better results. And basically, the math behind it is not as complex as it might actually look on the screen, because majority of these tasks are pretty pretty solvable and already exist in, I would say, in libraries and ready to use tools. So it looks kind of over sophisticated, but in reality it's all broken down into the functions with weights in the case of EKTOS model, and kind of metrics, search and comparison to typical mass metrics processing in CNN model, just to make it kind of simple and try to express it in 2 words. Okay, and that's and here on the right side you can see actually the detection. This pink bars, that's actually where we have the real cleaning, and you can see with this I don't know, violet small bar here, and the violet bar right after the first big pink bar is where the model is actually predicting that cleaning is happening. So you can see that in both cases actually we have pretty solid model hit into the real life situation. All right. Okay, so let's talk a little bit about how actually you can do this kind of projects, how to use all this modern and somewhat fancy technologies when you want to have a product based on TinyML model. Well, basically, as Darina already said, the first most important part is data collection. So you have to really understand your data. You basically, it's kind of simple. You understand. It's more or less like kids understanding the real world around us. We see, we smell, we hear the data, and that's basically how we collect these data collections. We can use later on to be able to classify specific events. And that's what you do as the very first step. This step you can do yourself in your product before you activate a data analyst to help you to label the data, or you can also describe use cases and let team like we have our data analyst team to make this data collection for you. Then we have model development, and then step number 3, that is actually sometimes complex because you have to really find a balance between model footprint and how fast it can be executed in your small embedded product. It is actually porting, and this is where we have some also limitations, especially for the really small embedded products. Libraries like TensorFlow Lite, they have some serious limitations. You can model, you can obtain and construct a model on a PC or in the cloud, like Dorina mentioned, AWS or Google Colab, and it would work perfectly fine. But then you go down to the small embedded target, and then you meet some constraints like memory availability, ability to do computations with fixed point only and stuff like that. And that's what is normally addressed during porting. Let's look into this process a little bit more in detail. So if you start the development of the product based on machine learning, well, like always, you obviously start with requirements clarification. That's what you need for any kind of project. And then already here, you can actually start using the software developer to be able to understand the architectural diagram of the system, what kind of sensors you have, what kind of connectivity your product must have, what kind of control objects you would control and stuff. And then obviously you have the data collection process. And here you can do it yourself as the product owner, or you can ask also your supplier to do the data collection for you. My recommendation obviously would be that for all product owners, you have the data collection process at least carried out a few times by yourself, because then you know your product better. Then you go to the data scientist part of the process, where you can see you have to do data preparation, labeling, pre-processing, so you can actually find those classifications, find those classes, clusters. There are different techniques how to group the data, you see, and group the data by some kind of logical, to let data belong to particular logical parts of the data sets. Then you do development of the model, and then you do model training and validation. And this process between model training and validation, model development, is actually cyclical, because if you train the model and during your validation, you can see that the score of your model, the ability of your model to actually find the particular event you're looking for is too low. Then you have to go back and actually change the model as well. So this is kind of the cyclical part of the process here. And then when it's done, when you can, say, well, the model seems to be all right, you're ready to move on. Then you go to the model porting and optimization. So that's where you do all those constrained porting to the small embedded target, do again verification on embedded system, as well as validation that your product works. So you actually solve not only what models tells you, but also you solve what your product brings as the business value to your clients. And then this can be also a pretty cyclical process. So if you don't see something happening right here, you go to the model simplification, or vice versa, using different libraries to control your model and stuff like that. And then apparently, if you model here down here, maintenance and updating, that's more like the whole life cycle of the model. If your model changes, if the data changes, because the real world behind the window changes every day, you have to go back and do data collection again. So that's what happens. The cyclical approach of development here actually fits perfectly well to the modern project management methodologies like Agile and Scrum. So you can definitely benefit if your team is already kind of into the modern sprint-based development and management techniques. Well, let's start wrapping up a little bit here. So what many people would say, okay, looks pretty good, but also pretty complex. Let's try to kind of wrap it up by analyzing if TinyML is something what you can use for your products. And the way we wanted to highlight it here is that, well, if you have a super simple and trivial task, let's say you're comparing one temperature and one set point, and you want to on and off a lamp or heating and whatnot, well, probably you can just synthesize the classical algorithm. You don't need to go to the machine learning solution. If you have some mission critical applications where you have to defend in terms of auditing the solution, in terms of certification and stuff like that. Normally this belongs to functional safety applications. It could be working with explosives. It can be controlling the the trains, airplanes and stuff like that. I think you shall probably as well go to the more classical algorithms, because you can, by simple techniques like greenlining, like assessing all the branches of the algorithms, you can actually defend your control system. And then if you have the last thing where ML solution would not really fit, is that if you really have a tiny amount of data, so you cannot actually base your model training on that data, because it's really, I would say, nothing to judge on. If you don't have these limitations, then you're good to go to the machine learning solution and benefit from kind of solving complex algorithmic problems in the data processing way. So that would be my recommendation. So let's wrap up. If we break down the process into 6 steps again, well, we just want to emphasize that step 1 is to know your data. So data is again here. Then you do the labeling process of your data. And for this, you can use your eyes. If you have a relatively small amount of data you want to analyze, you can use labeling tools. There are just, myriads of tools available for that. Then you do the good requirement specification about what actually you want to solve with your data analysis. What kind of anomaly, what kind of classification, what kind of regression you're looking for. What do you want to see when data is analyzed? Then you develop a model and fine-tune it to fulfill project requirements. You test your model. Then you deploy your model on a device and perform verification validation process, so you can actually defend the product value. So that's pretty good explanation, actually. Pretty simple 6 steps model how to manage your ML projects. I think that's mainly all about TinyML for today. What I want to, before we move to the Q&A session and the presentation of our next webinar, I want just to say a couple of words about EKTOS and the way we work with our projects. As I mentioned, we have three businesses inside EKTOS where we do development. As you can see here, and this is the department I'm representing this evening. We have our colleagues from test department who are testing and verifying that electronics is good to be ready for sales around the world. And then we have our next sister company called Tech Electronics, who are doing contractual manufacturing. So basically, EKTOS offers the full cycle of product development, from idea, from a napkin design to the mass scale manufacturing. That's what we like to do. That's where we feel we are good. And lately also, as you learn from this presentation, we have started to introduce machine learning in customer projects. That's where development kicks in and develops the products based on TinyML. So we will be happy to make this kind of solutions for you. So that would be really fun to try to tackle your complex tasks with data, classical data processing or big data processing and machine learning process. So now I have questions and answers. I think we'll have like 5 to 10 minutes for questions and answers. So I'm ready to listen to your questions. Just unmute yourself and push the question, or you can just write in the chat. I'll try to address that. just looked into the meeting chat, and I can see that only 2 people out of 28, we have actually 28 tonight, have been doing a little bit ML tasks. So I believe that was interesting to understand the majority of you. Okay, Sergey, you have a question? You can just unmute, or you can just put it in the text here.
Yeah, hello. So I have simple question. Have you considered the efficiency and performance of the processor while doing, for example, this cleaning example? So what kind of performance you are expecting to have from MCU to run this kind of tasks?
Okay, well, that's a good question. Actually, what is funny with these neural networks is that it's not, many people see the processing by neural networks as something super complex, like a cold fusion process. It's actually not. Basically, it comes into the very simple process of processing the data which are marked with weight coefficients, so to say. And then, as Darina shown, let me put up the slide of perceptron. Let me just find my cursor here. And
yeah, it's slide 17.
Yep. As you can see on this slide, as long as you have properly configured all these layers, then basically the data propagation, let's say you have a temperature, A1 as a temperature, and then this propagation through the layers is very simple data processing. It doesn't require any super complex math to be able to solve that, and that's the way you use the biases and weights to be able to have fast streamlined calculations. So it's not super complex. So it's relatively comparable to I would say to the classical computation algorithms, like kind of evals based algorithms, I would say. You had more questions, Sergey, or you mentioned few? Can hear now.
Yes, thank you. So I understand it now. No more questions.
Okay, there is a question from video. Hello, is there any interesting activities in verification validation process? Well, good question. I don't think that there is any specific particular difference from classical VNV, so to say, for the classical implementation based on the kind of prescriptive control logic. Because in VNV, you normally, well, I would say the validation or the verification of the model porting, that's important, because you really want to see that your embedded target calculates with the same precision as your cloud computing, so to say that. So you develop the model at a cloud, either this Google Colab you use, or AWS, or your personal PC if you have the the pretty solid one. And then you want to understand it on all the kind of data sets or all the variables you generate with your test scenarios. You have same performance at the cloud and a small target after porting. So that's the specific part of verification, if it works properly or not. And the validation, apparently, when it goes to the product features, I would say that's kind of the same, because if you want to stick to the user stories, like, okay, if I want, let me put out one, I want to have a cozy temperature at home when I get home after my office time, then apparently you have to analyze both with classical sequential algorithm, prescriptive sequential algorithm, and also with ML approach. You have to analyze if the temperature you're getting when you get back to your home, if it's cozy or not, if it's warm enough or not. So kind of validation from functional perspective gets to more or less the same. That's how I would describe it. We have one more question. how much time did the project I presented took from idea to release? Okay, well, I think because of us exploring two models at the same time, it actually took us quite a bit of time. I would say data generation was definitely a problem because we had to actually do proper cleaning, so to say, and improper as well. So you cannot really cheat the real world. If you want your model to be able to recognize some real events, you have to not simulate, but kind of make the events. That's kind of the way you do it. So we have been using our office premises here for cleaning, and yeah, we have the cleaning staff coming in here every second day, and that's basically the process, the data sets, the frequency of data sets we're having. So that's how it works. But I think regularly from the data sets being obtained and labeled properly, then the porting and testing of the model and kind of profiling the model, how fast we work and stuff, is pretty fast process. But the data capturing is a little bit more complex. I see, Darina, you raised the hand. You want to answer this one as well?
Yeah. What I want to add is that actually the data collection phase takes a lot of time because even now we are collecting more and more data and retraining model and reevaluating it because of course seasons changing, and sometimes when we change person who cleans the office, the behavior of our data also changes. So you should consider first your data and gather a lot of it before performing some ML solutions.
Yeah. So we will not be recognizing who is cleaning good or bad in this situation, because it's against the data privacy. So we are not going to punish any of the cleaning staff if they're cleaning differently. But that's also, yeah, exactly one of the interesting points, that data is data, and the real world evolves all the time. That's as well what you have to expect from a data model. That's why having the the firmware update, especially in the massive, I would say in the massive deployments of IoT products based on TinyML, must have firmware update over there, because you will have to you will face the changes of the model over time. That's obviously the problem. Okay, and we have one more question here. What is the size of the matrix of the model of this particular project? I don't know if you
if you mean weights and biases, sorry for interrupting, but
yeah,
if you mean weights and biases, it's
so.
a really huge one. I can send you if you want. Please, please type UML in the comment section, and I will send you the size. But it's big, believe me.
Okay, good. Well, let me then move. If we don't have more questions, let me then move to a little bit open up the idea of our next webinar. Well, we have one more question. I will get back to it, Jesper. The next webinar we are going to run would be actually practical hands-on use and ML implementation on two platforms. In this case, which we have presented to you during this webinar, we work with Espressif. ESP32 is one of the most well-known Steam platforms around the world, I think, and we will show kind of way more details how it looks from under the hood. And the second part of the webinar will be actually about using the same principles, but using slightly different tool chains that are provided by ST Microelectronics. They have two products, Nano Edge AI for really simple applications, simple models, and Cube AI for more sophisticated ML tasks. And as long as EKTOS as official ST partner will be most likely bringing in some ST news about their recent updates in the tools and what tools can do. It's actually pretty simpler for the simple models. This NanoEdge AI is really simple tool, and you will definitely love it when you see it. So that's what we're gonna run mid-November. So please sign up, and we'll be happy to kind of explain more how the things are happening in the ML. And before we shut down, I want to address the question Jesper is asking, how dependent is the model on sensors, and if the sensors changed, shall we do the full retraining? Darina, do you want to take this one?
Yes, of course, we shall do the full retraining because we are looking at a certain type of data. For example, if we have 5 sensors, which is related humidity, Vox, CO2, ambient light, and other, and we train the model on it, the model will examine patterns in these particular sensors. And if you change some sensor, of course, the pattern behind the data of this sensor, for example, we will add, I don't know, pressure sensor or other, we will, of course, need to retrain the model and show this new data, because a model has never seen this data before, and it will be impossible for it to make some assumptions and make some decisions.
At the same time, thanks, Darina. At the same time, I want to say is that if you change the sensor that has the same resolution and same, accuracy, I believe it will be kind of, the same for the model. Even if the data is, I would say, if the data is sampled with the same sampling frequency, same accuracy and resolution, we can even get the data from a remote host. And as long as it's fitted properly into the same model, I believe it will take either no retraining or minor retraining.
No, it won't work if you're trying to change temperature with some other metric. It just won't work because of characteristics. For example, if you hit something, you know that it's hitting. But if you make pressure on the device, the model won't say that it's hitting because it's simply different nature of data. So
yes, that's clear. What I was referring to is to kind of replace one temperature sensor with another temperature sensor.
Yeah, of course. Yes.
That would work fine, even if this temperature comes from a, let's say, Bluetooth sensor that is outplaced from the box, but just there. Of course, if you get a temperature from Denmark for the product that is placed in Northern America, then it's obviously a small problem to assess the cleaning process. All right, that was the last question for today. So, well, thank you everyone for attending this great webinar this evening. Thank you, Darina, for your complex math explanations of different models. That was hard but interesting to understand.
Thanks for having me.
Great, and I'm really happy to have all of you. We will be sending the specific feedback form, and to make our webinars better, I would really want you to respond to that feedback form, and then for those who are responding, we'll be sending slides and the presentation. So thank you very much once again, and I believe you can enjoy your evening. Thank you.
Thank you.
Yeah, thank you.
Thank you. Bye,
Thank you.
everyone.